Welcome to Knowledge Search channel. In this video, we will be discussing about problems in rectifier. As you all know, what is a rectifier actually? Rectifier is an electronic circuit which can convert AC signal to a DC signal. From the inception, there are two types of electrical signals. One is the AC signal, the other one is the DC signal. DC signal are used used for charging the batteries, and during the discharging also DC will be there. Whereas AC will be used in normal electrical machines, tube lights, and other household applications. Mainly for battery charging, and in few of the industrial applications we use DC. So, wherever we want to use DC, we have to convert the AC to DC. So, this particular function is carried out by an electronic circuit which is called as rectifier. Okay. There are many types of rectifiers available in market, okay, and we will be in this video we will be discussing about the main discussion is about the problems. Okay. The main discussion is about problems, but I will be just giving you some of the introduction of what are the different types of rectifiers and what are the plus and minus of each and every rectifier, and which rectifier was more advantageous. And finally, we will be closing this video with one of the problem in half wave rectifier and a design problem in full wave rectifier. So, this is what the entire video is all about. So, without any further delay, let us go into the further discussions on rectifier. Okay. So, as you all know, what is a rectifier? A rectifier is nothing but it will be having a PN junction diode. Okay, it will be having a PN junction diode, and you know that what is the function of PN junction diode? The function of PN junction diode, it will be conducting only in one direction. That is, only if it is forward biased, it will conduct, and when it is reverse biased, it will not conduct. Okay. And this particular concept is being used for conversion of AC to DC supply in the rectifier circuit. Okay. So, rectifier is a device which converts AC to DC, okay, using the PN diode. Okay, using the PN diode. Okay. So, basically we classify this into two different types. One is half wave rectifier, the other one is the full wave rectifier, and again full wave rectifier, again it is classified into two types. One is called as the center tapped one, the other one is called as the bridge type. As you all know, the bridge type is the most advanced type when compared to the previous ones. Okay. So, half wave rectifier, it is very cheap, but it is having some drawbacks like the efficiency is very less and the ripple factor is very high. So, these things make this half wave rectifier not to be used in quality applications. Okay. So, whenever you need a high precision output and better efficiency, we have to go with full wave rectifier, but whenever the cost is the main concern, then we have to go with the half wave rectifier. Okay. So, again in full wave rectifier there are two types, one is the center tapped one, the other one is the bridge rectifier. Okay. So, nowadays center tapped one is used only in high power applications, whereas bridge rectifier is more suitable for low power applications. As well, for miniature circuits, bridge rectifier is the most suitable one when compared to the center tapped one, because center tapped one will be having more volume and weight, but it will be better to have center tapped configured for high power applications when compared to the bridge one. Okay. So, this is what the entire discussion will be all about. Okay. So, now we will be discussing about how it works. Okay. So, let us go into the comparison. So, comparison of rectifier circuits. So, as we have discussed, the first one is half wave rectifier, then full wave rectifier. So, this is the circuit diagram. Okay. So, initially you will be having a transformer, it will be a step down or step up transformer, but more normally it will be a step down transformer if we need for low power applications. Okay. So, step down, and then we will be having only one diode. Okay. So, here you will be having only one diode, and So, you can see that whenever this diode is forward biased, so you can see that so here the phase neutral will be changing in alternative fashion. Okay. So, whenever the positive cycle is there, okay, this diode will be forward biased, whereas during the negative cycle the diode will be reverse biased. So, as we have already discussed, whenever it is in forward bias condition, the diode will be starting in conduction mode, whereas in reverse bias condition the diode will not conduct. So, here you can see that the output will be having only the positive waveforms, whereas the negative waveform is being clipped. So, this is also one of the type of the DC waveform. The DC is nothing but will be having only either positive or negative. So, if you have only the positive waves, then it is a DC waveform. But this is not a pure DC because the ripples are very high. A pure DC is nothing but a straight line. But here you can see that you are having some, that is the sine wave, not the sine, the half sine wave is there, and so the ripple factor is quite high in case of the half wave rectifier. So, this makes the half wave rectifier, the efficiency will be highly reduced in case of the half wave rectifier because of high ripple content, okay, and losses will be there. So, in order to achieve a better efficiency and in order to have a very low ripple factor, then they came out with a better solution which is called as a full wave rectifier, and this is called as center tapped configuration, and you can see that the transformer here it is a step down transformer, whereas here you can see that it is a center tapped configuration. Why it is called as center tapped is because in the secondary center I am going to connect this load at the secondary center. Okay, the center is, that is the load, this is the load, RL is nothing but the load resistance. Okay. So, this RL is being connected to the center of the secondary. So, this is what you want to remember. Okay. Whereas diodes are connected on the both ends of the secondary. Okay. So, that is why it is called as center tapped. Why it is called as center tapped? So, tapping is nothing but, so at the center I am going to take the, so this is a special type of transformer, so which adds to additional cost also, and also the volume will be quite high when compared to the normal transformers. So, as you all know, here two diodes are used. So, during the positive cycle, this upper diode will be in forward bias condition, and so the output across the load will be there. So, since it is forward biased, it will start conduct. Whereas during negative of cycle, the upper diode will be reverse bias condition, whereas the lower diode will be in the forward bias condition, and because of which the that is the flow of current will be in the same direction in the load resistance, and you will be the negative will be converted to positive, and finally you will be getting the output something in a similar way like this. So, when compared to half wave and full wave, the only difference is you can see that the negative cycles are clipped in the half wave, whereas in case of full wave the negative cycles are converted to positive cycles. So, this is the most advantageous because you know, in case of half wave, since the negative cycles are being clipped, you can see that the losses are very heavy, okay, and also the efficiency is lost because of it. And so, whereas in case of full wave, you can see that the negative is also being converted to positive, and because of which the efficiency is quite best. Okay. So, but the main problem here in case of the center tapped configuration is the transformer is itself something new, as well the weight of the transformer is quite heavy when compared to the normal transformer. So, and also quite costly, the manufacturing cost is quite high. So, in order to avoid all those things, we are going into the next version of the rectifier circuit, which is called as the, again this is also a full wave rectifier, and this is called, why it is called as half wave is because only half of the AC input is being converted to the output. That is why it is called as half wave rectifier. Whereas in the second type and third type, you can see that both the cycles of the input, okay, whereas you can see that positive cycle as well as negative, both the cycles are converted to positive cycles. So, that is why it is called as full wave. So, here it is called as half wave because only the positive cycle is being converted to and given at the output, whereas negative cycles are clipped off. Whereas in case of full wave, both the positive and negative are used. That is why it is called as full wave. Whereas in case of bridge, you can see that there is no center tapped configuration is not needed. Only thing is the positive is connected in this fashion. Okay, so here this diode direction is very, very important. Okay, so it should be something like this. Most of them in many of the answer papers, I can see that this diode direction, if it is wrong, it will not work correct. Okay, so please remember it. Okay, so this is a very important thing you want to remember. Okay. So, here you can see that whenever, so again you can see that when during the positive of cycle, this diode that is this diode, that is diode on the right side as well as diode on the left side, these two, you know, these two will be in the forward bias condition, and because of which you will be getting a positive cycle. Whereas during the negative of cycle, what happens is the diode here, okay, this diode, that is the diode on the lower side as well the diode on this side, that is left side. So, this will be in forward bias condition, because of which you will be getting the negative cycle is also being converted to the positive cycle. So, finally, what happens is both the positive and negative are being converted to positive cycles, and because of which you are getting a DC output voltage in all the three cases. The main advantage of the full wave rectifier is, since both the cycles are being converted to positive cycles, the output voltage is better, okay, that is the ripple content is quite less, the efficiency is quite high. So, that is the main advantage. Only thing is the cost is quite high, because this half wave rectifier is very simple. Just by using a simple one diode you can convert it to a DC, but here you can see that you will be using two diodes with center tapped configuration. Again the circuit complexity is quite high when compared to the half wave. So, this is the main drawback with the full wave rectifier. The circuit complexity is quite high, whereas the efficiency is best. Whereas in case of half wave rectifier, the circuit there is no complexity because you are using only one diode. So, but the problem is efficiency is quite compromised. Okay, it has to be compromised, or it is less. As well, the cost is also less in case of the half wave rectifier, because the number of components is also less. So, next you can see, so these are some of the parameters for comparing this half wave, full wave and bridge rectifier. So, you can see that the number of diodes used in half wave rectifier is 1, as you can see that only one diode is used, whereas in case of full wave rectifier the number of diodes are 2, that is, this is a center tapped configuration. Okay. Next, in case of bridge configuration, the number of diodes used as 4. So, these are all the formulas for the derivations and other things. You can refer the books, okay, but this formula is very much needed for solving the problems, because the problems are very important for your examinations. So, because of which please remember these formulas. So, it is very simple to remember. For example, if you take the average DC current, so here you can see that pi, okay, the denominator will be pi in all the cases, whereas for full wave it will be multiplied by 2. See here for average DC current it is Im by pi for half wave, it is 2 Im by pi for full wave. Similarly, again mostly for half wave and full wave the expression remains same, because the output waveform is similar for both full wave center tapped as well as the bridge configuration. Similarly, you can see that for average DC voltage, okay, so they will be asking find the DC voltage. So, they will be giving the value of EM. IEM is nothing but, so this is the maximum value. So, sometimes in problem they will be giving you the RMS value. If the RMS value is given, you have to multiply it by √2 in order to get the maximum value. Similarly, EM is nothing but the source voltage. So, source voltage again it is a maximum voltage. So, whatever RMS voltage is given, that you have to multiply by √2, okay, in order to get the maximum voltage. So, that is maximum voltage will be equal to RMS voltage into √2. So, normally in problems they will be giving the RMS value. So, you have to multiply by √2, that is very important. So, you will be getting this ESM by pi in order to get the average DC voltage, as well as 2 EM by pi for average DC voltage for the full wave rectifier. For bridge configuration it is again 2 EM by pi, because the wave shapes are same for both center tapped and bridge configurations. So, next is RMS current. You can see that in case of half wave it is Im by 2, whereas in case of full wave it is Im by √2, and again in bridge also it is Im by √2. Again you can see that the DC power output. So, here you can see that the DC power output is 4 times when compared to the half wave expression. You can see that in this case DC power output, that is half wave configuration, Im square into RL by pi square, whereas here you can see 4 into Im square into RL divided by pi square. So, 4 times, okay, you are getting the DC power output 4 times. That is why the efficiency is very best in case of the full wave as well as the bridge configuration, the expression remains same. So, again AC input power. So, how much input I am giving. So, this input power and output power is needed in order to calculate the efficiency, because the efficiency formula is output by input. So, you have to calculate what is the output power, you have to calculate what is the input power, and output power by input power directly gives you the efficiency. And from this expression you can see that the output power is high for both full wave and bridge configuration, because of which the efficiency should be high. Okay. So, here you can see that AC power input is nothing but Im square into RL plus RF plus RS. So, what is the 3 resistance are there? So, this 3 resistance, so RL is nothing but the load resistance, RS is nothing but the source resistance of the transformer, and RF is nothing but the forward resistance of the diode. So, these things can be found out from the data sheets, or they will be giving you in the problem. Okay. So, RL plus RF plus RS whole divided by 4, Im square into RL plus RF plus RS whole divided by 4. Here also you can see that AC input power is quite less, Im square into RF plus RS plus RL divided by 2. So, you are getting you can see that in full wave configuration the input power taken is very less, whereas the output power is high. Okay. So, just by changing the configuration, the circuit configuration, you can see that the efficiency is very highly improved, drastically improved. That is the advantage of the full wave configuration, because of which we are going for the full wave configuration in most of the circuit nowadays, in order to achieve the maximum efficiency and better quality output. Okay. So, now let us move on with some problem solving. Okay. So, problems in half wave rectifier, then we will discuss one of the design problem in full wave rectifier. Okay. So, problem in half wave rectifier. So, I will just give you one problem. Okay. So, you can just see that a half wave. So, you can just see this. So, this is the problem. So, here you can see that a half wave rectifier having a resistive load of 1000 ohms. So, here you can see that it is 1000 ohms. Okay. So, here you can see that it is 1000 ohms. Okay. And here it is rectifying an AC voltage of 325 volt peak, is it right? So, here you can see that. So, I am using 1000 ohms as the RL. So, this is the RL is 1000 ohms. So, it is I am just underlining here. And what is the input voltage? So, input voltage given is 325 volt. Okay. And the diode has a forward resistance. So, they are giving the forward resistance as 100 ohms is there. Okay. The forward resistance is very high, around 100 ohms is there. So, now what we have to calculate? So, we have to calculate what is the peak, average and RMS value of the current. So, we want to calculate the peak, RMS and average value of what is the DC output power, okay, and what is the AC input power. And if you know what is the DC output power and AC input power, directly you can find what is the efficiency of the rectifier. So, all these things we have already discussed the formula, okay. So, just a substitution of what are the data that are available. So, you can see that what will be the total resistance. So, in order to find, okay, in order to find the peak current, what you want to do is, I want to find what is the peak voltage. The peak voltage is already given. As I have already told, if peak voltage is not given and RMS value is given, you want to multiply it by root 2 in order to get the peak value. But peak value is directly given. So, you can see that it is the very simple. So, peak current will be equal to peak voltage divided by total resistance. So, total resistance is 1100 ohm. Why it is 1100 ohms? Because the total resistance will be diode resistance plus load resistance. Since source resistance is not given, it will be taken as negligible and can take it as 0. So, now 325 divided by 1100. So, you will be getting the answer as 0.295 amps. Okay. So, now the next question is average current. So, how to find the average current? So, it is also very simple. Already we have discussed the formula. It is nothing but peak current divided by pi. Okay. It is nothing but peak current divided by pi. So, what is peak current? So, here you can see that peak current is nothing but already we have found out. So, this value. Okay. So, this value I am going to just substitute here. Okay. So, here and divided by pi. So, your answer is 0.094 amps. Now, what is the RMS current? So, already we have discussed. So, this is the formula. So, IRMS will be equal to I peak divided by 2. So, this is the formula. Okay. So, this is the formula. So, in this formula, so I peak divided by 2. So, again, so you can see that IRMS will be equal to 0.295. So, I peak is nothing but 0.295, which has been substituted over here, divided by 2. So, the answer is 0.147. So, it is very simple. Okay. It is very simple. So, if these problems are asked, you can see that you can directly get the answers by substituting the values. Okay. So, you have found out the first subdivision, that is A subdivision has been done. That is, I have found out what is the peak value, what is the average value, what is the RMS value of current. So, the next subdivision is I want to calculate what is the DC power output. So, we will move on to, okay. So, what is the DC power output? So, DC power output is nothing but you have to take the average value. So, okay. So, I average square. So, this is the formula. Okay. So, this is the formula, that is I average square divided into R. So, IR, that is I square R. I square R is nothing but the power, always you know that. So, you have to take the average value. So, from the previous thing, you can see that the average value is average value of current is 0.094 amps square into 1000, that is R load is 1000 ohms. So, we will be getting the answer as 8.84 watts. Now, what is the value of AC input power? So, AC input power is I RMS square you want to take, because DC output power you can take it as I average. So, this is where some mistakes may be done. So, for DC output power always you have to take the average, whereas for AC input power you have to take only the RMS value. So, I RMS square into R diode plus R load, because in input side you can have diode is also there, load is also there, whereas in case of output you will be having the load resistance only is there. So, whereas in case of input you are having the diode and R load is also there. So, that is why I have included 100 ohms plus 1000 ohms, whereas in previous case I have not included that 100 ohms. Okay. So, finally, you can see that you will be getting the answer as 24 watts. So, IRMS is previously we have calculated as 0.147 in the previous calculation. Okay. So, whereas I average is 0.094 and IRMS is 0.147. So, finally, you got 24 watts. So, similarly, how to find the efficiency of the rectifier? So, efficiency of the rectifier is nothing but the output DC output power divided by AC input power. Okay. So, the rectifier is going to convert to AC input power to the DC output power. So, always the formula for efficiency is output divided by input. So, DC output power divided by AC input power. So, DC output power is nothing but 8.84, okay, and AC input power is 24. So, you can see that I have substituted over here 8.84 divided by 24, and finally, I have got the answer as 36.9%. So, this is the only percentage. So, efficiency is very less. Okay. So, finally, you can see that the peak current is 0.295 amps, average current is 0.094 amps, and similarly, the RMS current is 0.147 amps. So, these are the answers which we have obtained. So, similarly, DC output power is 8.84 watts, AC input power is 24 watts, and efficiency is 36.9%. So, similar type of problems might be asked in many of the question papers. Okay. So, only thing is the values will be quite different and you have to substitute. Okay. So, next is a real time design problem we will discuss. So, real time design problem is for full wave rectifier. So, until now we have discussed about the half wave rectifier, and now we are going to use it for the full wave rectifier. So, how we can design? So, normally you can see that in mobile chargers and in a car and vehicle you are having the chargers, you are having the battery. In order to charge the battery, we are using one charger circuit. For the charger, we will be using a full wave rectifier configuration. So, how to design it actually, and what are the different components in the full wave rectifier in a practical design application is what we are going to discuss from now on. So, here the question asked might be something like this: design a circuit diagram for a DC charger that converts, okay, you can see that converts a 230 volt AC source to a 5 volt DC output using a full wave. You can see that full wave using a full wave DC, that is full wave rectifier, bridge rectifier we want to design. Okay. So, what are the components that has to be used? So, the first one is transformer. Okay. So, in the transformer I am going to step down to 12 volts, because normally the transformer range is either 12 volt or 24 volts will be available. So, since we are going to use only the 5 volt, so a step down transformer with 230 volt to 12 volt is being used. Okay. Next is I want to use a full wave bridge rectifier. So, which is going to convert the AC voltage to pulsating DC voltage. Is it right? So, is it okay? But charger the DC voltage will be pulsating. What is it pulsating? It is just changing with respect to time. So, that has to be converted to a smooth output, that is a constant DC output, that can be done by means of the filter capacitor. Okay. So, the filter capacitor is used to produce the smooth and stable output. And finally, we are using this regulator. Okay. So, this regulator is called as the 7805 regulator. So, what is the use of this regulator is whatever may be the change in input, the output voltage will always be maintained at 5 volt DC output. So, this is how you want to construct a full wave bridge rectifier using the above components. So, we need 4 different components. One is the transformer, the other one is the bridge rectifier, next one is the filter capacitor, and then the voltage regulator. So, how it works? So, the AC step down voltage, you can see that, so these are all the working principle, that is the 230 volt is fed to the primary winding of the transformer, and the secondary winding produces the lower output voltage of 12 volts. And then we want to rectify using the full wave rectifier, which is going to convert the AC voltage from the transformer to a pulsating DC. So, since it is a pulsating DC, we want a smooth DC, which is going to improve the efficiency of the load, and because of which we are using a filter capacitor, and normally an electrolytic capacitor is preferred, okay, which is going to smooth out the ripples of the pulsating DC, and so that the output voltage is stable. So, there will be some fluctuations in the input voltage. In order to make the output voltage stable, even when there is a fluctuation in the input voltage, we want to use a voltage regulator. So, this is a voltage regulator. It is an IC voltage regulator which is called as 7805. So, this 05 is nothing but which means that the output voltage will be maintained constantly at 5 volts. So, that is why it is called 7805. Okay. So, this is 7805. So, next let us go into the circuit. Okay. So, you can see that this is the circuit. Okay. So, you are using a transformer. Okay. So, here you are using a transformer as we have discussed, and 1 amps fuse is there. Okay. So, here you can see that 1 amps fuse is there in order to protect the entire circuit if there is any fault or something like that. And this is the rectifier circuit. So, this is the half wave rectifier, that is the full wave rectifier circuit, full wave bridge rectifier. Okay. So, this is the full wave bridge rectifier. And you know what is the use of this 470 microfarad? So, this is used for, this is the filter. Okay. This is the filter. Okay. And again this is the regulator, that is the voltage regulator circuit, that is in small short it is called as voltage VR. So this is, you can see that 7805. Okay, so why we are using 7805 is, you can see that there will be a constant of 5 volts. Okay, the 5 volts will be there. So this is how normal DC charger circuit for your mobile phone. Okay, this is a design actually. So if you just cut open your charger circuit of your mobile phone, it will be having a similar structure, something like this. Okay, so we will be having a transformer, you will be having a full bridge rectifier. So this transformer is used to step down, and similarly the full bridge rectifier is used to convert the AC to DC. So here you will be getting the DC. Okay, in that here you will be getting a pulsating DC, and here you will be getting a pure DC. Okay, here you will be getting a pure DC. Okay, here the pulsate DC with some ripples will be there. Okay, so at this point you can get pure DC, but in order to get a constant plus 5 volt, I am going to use this 5 volt regulator. So finally you will be getting a constant output voltage. Even if there is an input fluctuation, this IC regulator will be maintaining the output voltage constant at 5 volts. So this is what the discussion is all about. Hope you are all clear with the design. Okay, and I am sure this video would have given insight into how to design a rectifier for both half wave as well as the full wave configuration, and I am also confident that I have given you enough explanation related with how to solve if such questions are asked in the university question papers. Okay, so thank you very much for your patient listening. If you really like this video, give a thumbs up, and any comments you have, you can just post it. And if you feel that this video will be useful to someone, you can just share it. And if you feel that whatever videos I am just posting in my channel, it is useful, you can just subscribe to my channel. Thank you all once again. Thank you.